Welcome, everyone. Today, we're diving into the critical role of hospital HVAC systems. Our presentation is titled Hospital HVAC, a medical life support system, and it emphasizes that these systems are not just about comfort, they're essential for patient safety and infection control. We'll explore how the design must adhere to standards like SBC 501, ASHRAE 170, NFPA, MOH, and CBAHI, and how every HVAC decision is treated as a clinical safety decision. Ultimately, we'll see how hospitals are engineered as pressure-controlled, filtered, and zoned environments to support optimal healthcare outcomes. A 200-bed hospital HVAC system is classified as a medical safety system. This means it plays a critical role in ensuring patient and staff safety by controlling the environment. HVAC controls are essential because they help manage infection spread, speed up recovery times, and prevent airborne contamination. Think of pressure, filtration, and air change rates as clinical tools, like instruments in a doctor's kit, that help us maintain a safe and healthy environment. Teaching HVAC without considering zoning and pressure control is like doing half engineering. It's incomplete and potentially dangerous. Proper zoning and pressure management are vital because they directly impact infection control and overall safety in the hospital setting. So, understanding these elements is key to designing a truly effective HVAC system that supports patient care and safety. Let's talk about how hospitals are divided into different zones: critical, semi-critical, and non-critical. Each of these zones has its own independent pressure and filtration logic, which is essential to maintaining a safe and controlled environment. It's important to note that Saudi authorities require these zones to be approved during the design stage. This approval, often referred to as MOH approval, ensures that the zoning is correctly planned from the very beginning. Zoning is not just a recommendation. It's mandatory before we start routing ducts, performing load calculations, or scheduling equipment. If we treat the entire hospital as a single HVAC zone, it can lead to critical design failures, especially in infection control. Proper zoning creates infection barriers and ensures each area has the right pressure levels, which is vital for patient safety and overall hospital performance. So, understanding and implementing these zones correctly is a key part of the overall safety and functionality of hospital HVAC systems. When we talk about sensible load, we're referring to the heat that comes from sources like people, lighting, equipment, and even solar gain. These are the factors that directly affect the temperature of the space. On the other hand, latent load involves moisture, which comes from respiration and fresh air intake. It's important to account for both because they influence how we size our cooling systems. Typically, we consider an air change rate, or ACH, of about 6. This means the air in the space is replaced roughly 6 times per hour, and we usually maintain a positive pressure to the corridor to prevent contaminants from entering. Now, when calculating the heat removed, or Q in BTUs per hour, we use this formula. Q equals 1.2 times CFM times delta T essentially. This helps us determine the cooling capacity needed based on airflow and temperature difference. And don't forget, when we're balancing the air, the exhaust from toilets must be included. Proper air balance ensures good indoor air quality and helps maintain the right pressure relationships throughout the building. All these factors are interconnected and crucial for designing an efficient and effective cooling and ventilation system. Let's talk about the specific requirements for ICU air quality and pressure management. First, the ACH, or air changes per hour, must be at least 12. This ensures rapid removal of contaminants and maintains a clean environment. In addition, the filtration system needs to include MERV 14 filters combined with HEPA filtration, which is crucial for capturing very small particles, including infectious agents. It's also essential that the pressure in the ICU remains positive relative to the corridor. This positive pressure acts as a protective barrier, preventing contaminated air from flowing out into other areas. To be precise, the pressure differential should always be at least plus 2.5 pascals, ensuring a consistent flow of clean air outward. Another important point is that fan coil units are not permitted in ICUs. Instead, all air must come from dedicated air handling units, or AHUs, specifically designed for this purpose. This dedicated supply helps control airflow and maintains the strict infection control standards outlined by guidelines like ASHRAE 170. Altogether, these measures are vital to creating a safe, controlled environment in ICUs, which is a key part of our overall infection prevention strategy. When it comes to isolation rooms, one of the most critical factors for safety is maintaining negative pressure. This means the air pressure inside the room must be lower than that outside, which helps contain airborne contaminants and prevents their spread. To achieve this, the air changes per hour, or ACH, should be at least 12, ensuring a continuous flow of fresh air and effective removal of potentially infectious particles. It's also essential that all exhaust air is discharged directly outdoors without recirculating it back into the building. This prevents any contaminated air from re-entering the environment, which is a key aspect of airborne safety and containment. Another important point is that the exhaust airflow must always be greater than the supply airflow. This slight excess ensures a negative pressure is maintained consistently and no contaminated air leaks out. Makeup air, or the fresh air replacing what's exhausted, should only come from the corridor. This helps maintain proper pressure balance and prevents unintentional air mixing. Finally, shared exhaust systems are strictly prohibited for isolation rooms. Using dedicated, separate exhaust systems minimizes the risk of cross-contamination between different areas, which is fundamental for effective containment and protecting both staff and patients. Let's talk about the key environmental requirements for operating rooms. First, the air changes per hour, or ACH, needs to be at least 20. This helps ensure a steady flow of fresh, sterile air to reduce contamination. The room must also have positive pressure, meaning air flows outward, preventing contaminants from entering. Temperature should be maintained between 20 and 23 degrees Celsius, with relative humidity kept between 40 and 60%. These conditions are crucial for both patient safety and staff comfort. A critical feature is the laminar airflow, which must be positioned above the surgical table. This stream of filtered, sterile air flows smoothly in a single direction, minimizing turbulence and airborne contaminants right where the surgery happens. Peripheral low-level exhausts play a vital role by removing any contaminants that might escape the sterile zone, helping keep the environment clean. And finally, to achieve the required airflow, we use the CFM calculation, room volume multiplied by ACH divided by 60. This helps us determine the appropriate airflow capacity needed for the space. All of these elements, ACH, airflow patterns, temperature, humidity, work together to create a safe, sterile environment essential for successful surgeries. In the Saudi climate, one of the most significant factors affecting cooling loads is fresh air. Summer outdoor air temperatures can reach as high as 46 to 48 degrees Celsius, which is quite extreme. This means that when we bring in outdoor air, it has a substantial impact on our cooling requirements. The ventilation load, which we often calculate using the formula Q equals 1.08 times CFM times delta T, essentially tells us how much cooling capacity we need to handle the incoming fresh air. If we underestimate this ventilation load, it can lead to serious problems like overloading the chillers or even system failures during peak times. That's why it's crucial to always include fresh air in our plant sizing calculations. Properly accounting for this ensures our HVAC systems operate efficiently and reliably, especially in such challenging climates. This concept ties back to the overall theme of designing robust and effective AHU systems that can handle the demands of the environment while maintaining indoor comfort. Now, let's look at how we determine the total load for the chiller plant. We use this simple formula, TR equals the total load divided by 12,000. This helps us size the equipment properly and ensures efficiency. Next, when we talk about pump head, H, it's made up of three main components: static head, friction losses, and a safety factor. The static head is the height difference the pump needs to overcome. Friction losses account for the resistance in pipes and fittings, and the safety factor provides some extra margin for variations or future expansion. It's also crucial to remember that the system requires both duty and standby chillers. Redundancy is key here, so if one chiller goes down, the other can take over seamlessly, maintaining continuous operation. Hydraulic separation is mandatory in these systems. This means we keep the chilled water circuit hydraulically isolated to prevent disturbances or pressure drops from affecting the entire system. Finally, emergency power must be capable of feeding at least one chiller and all essential pumps. This ensures that, even in a power outage, our critical cooling functions can continue without interruption, protecting the entire facility. All these points tie back to our overarching goal of reliable, efficient, and resilient chiller plant operation. Let's talk about ductwork integrity. It's crucial that all duct systems meet the SMACNA leakage classes to ensure minimal air loss and maintain efficiency. This helps us keep the system sealed and functioning properly. Next, it's important to remember that no flexible ducts should be installed before the HEPA filters. Rigid ducts are preferred here because they create a more reliable barrier and reduce the risk of leaks, which is especially critical in sterile or sensitive environments. All insulation used in the system must be vapor-tight. This prevents moisture from penetrating the insulation, which can lead to condensation, mold growth, and even infection risk, something we certainly want to avoid. Fire dampers play a vital role in safety. They must always be accessible for inspection and maintenance, so in case of a fire, they can be quickly operated to contain the spread of smoke and flames. Finally, vapor leaks are a serious concern because they can cause condensation within the ducts. This not only damages the system, but also promotes mold growth and increases infection risks, undermining the integrity of the entire environment. By paying close attention to these details, duct sealing, proper filtering, insulation, and fire safety, we ensure our systems are safe, efficient, and compliant with the highest standards. Let's now discuss the mandatory documents that are essential for ensuring quality and compliance throughout the project. These include shop drawings, technical submittals, MERV or WIR reports, the inspection test plan, as-built drawings, and operation and maintenance manuals. Each of these plays a crucial role in documenting the work and verifying that everything is in accordance with project specifications. In addition to these, TAB and DOP test reports are also required to validate the testing and commissioning processes. It's important to note that commissioning cannot start without an approved inspection test plan, or ITP. This plan sets the framework for quality assurance and control, ensuring that all tests and inspections are properly planned and executed. Finally, remember that documentation is not just paperwork, it's the legal proof of compliance. Maintaining thorough and accurate records helps safeguard the project and demonstrates that all work has been completed to the required standards. This underscores the critical role of QA/QC in our overall project success. Now, let's talk about the key tests involved in the commissioning process. These include air balancing, which ensures that airflow is properly distributed throughout the space, and room pressurization to maintain the correct pressure differentials. Smoke visualization is also critical, as it helps us verify the effectiveness of the airflow patterns and containment. HEPA integrity testing is essential for confirming that the filtration systems are working correctly and safely. Additionally, BMS trend logging allows us to monitor system performance over time, providing valuable data for ongoing assurance. It's important to remember that final acceptance of the system isn't just about passing these individual tests. The approval comes from several authorities, including the consultant, civil defense, and the Ministry of Health. Their review ensures that all safety and compliance standards are met comprehensively. And let's emphasize that performing TAB alone isn't the ultimate proof of safety. It's a vital step, but it must be complemented by thorough inspections, documentation, and approvals to truly confirm that the system is safe and operational. This holistic approach is key to ensuring the safety and effectiveness of the entire environment we're working to create. Now, let's talk about the key steps in our testing checklist. First, we perform airflow verification at all diffusers to ensure that the air is distributing evenly and properly throughout the space. This is crucial because any imbalance can affect air quality and system efficiency. Next, we validate the pressure levels using manometers, which helps us confirm that the pressure differentials are within the desired range. Maintaining correct pressure is vital for system performance and containment. We also conduct smoke tests to verify airflow direction. This simple yet effective method shows us exactly where the air is flowing, ensuring it moves as intended. For our HEPA filters, we perform a DOP test on each one. This test checks the integrity and proper functioning of the filters, which is essential for maintaining a sterile environment. Finally, we monitor the building management system continuously for 72 hours. This extended observation helps us identify any fluctuations or instability in the system, ensuring everything remains stable over time. All these steps, from pressure validation to continuous BMS trend analysis, tie back to our overall goal, ensuring a safe, efficient, and reliable environment. When it comes to hospital HVAC systems, operating without proper zoning is simply unsafe engineering. Zoning ensures that different areas of the hospital maintain appropriate air quality and pressure, which is critical for patient safety and infection control. Pressure control, in particular, is non-negotiable. It's not just a technical detail, it's a fundamental safety barrier that protects patients from airborne contaminants and helps maintain a sterile environment. Commissioning should never be viewed as an afterthought or a final step. It's an integral part of the design process. Proper commissioning verifies that the HVAC system performs as intended, ensuring system integrity and safety before the hospital is operational. Think of a 200-bed hospital HVAC system as a vital medical safety barrier. It's not just about comfort, it's about safeguarding patients' health. And remember, any shortcut taken in HVAC design or installation can turn into a clinical risk. Cutting corners might save time or money initially, but it could compromise patient safety and lead to serious consequences down the line. Ultimately, this all ties back to engineering ethics, our responsibility to prioritize safety and system integrity at every stage. Ensuring robust, properly commissioned HVAC isn't just good engineering, it's essential healthcare.